Hello, I'm Paul Crush, and I wanted to go over one of the key algorithms I use to find the orientation of coins. I call it rotational correlation. If this was documented somewhere, if there's a paper out there, I haven't really been able to find this. Please let me know, and I can point people to to a little bit better defined documentation. But at this point, I just wanted to throw something quick out there, so at least there's some definition or explanation of what the code is doing. So let me give you a few reasons of why this algorithm is important to me. Number one, I mean, you can group a collection of parts in a unsupervised fashion. You can find the orientation, in the same tool, and also it works as a rejection, or it lets you know if something doesn't match. What you're looking at in the screen behind me is groupings of coins that were grouped by using this algorithm. One coin was randomly chosen as a seed, the first one in the batch, and others are attracted to that seed, and that is the seed that they're most attracted to. So if you remove the seed, they would go into other categories. This was done in an unsupervised fashion, which is really cool because you automatically created these categories and groupings, and you got orientations for free. So a good example of the rejection aspect of it is, say for example, this grouping of coins. One of the things I did is go back and say, okay, so everything on the lower limits here of what the result total is, these probably don't match. Let's go ahead and make new groupings and see what matches to these lower resulting items. Hey, let's talk about the implementation of this algorithm. The first step is creating a model of the seed image. This model is trained, standard Linnet, convolutional neural network model. I'm using a Cafe deep learning framework. It's trained with 360 different classes. Each one of those classes correspond to a 1 degree difference in the rotation of that single seed coin image. So it's self-referential. It's based on that one image. Not a bunch of different coins or different classes of coin. So the output that you're desiring here is twofold. First, you want to know the angle, the difference angle, the majority difference angle of your test coin to your seed image. And the other thing that you want to know is, what's the probability of that? So in all 360 tests, you want this angle difference, okay? And that angle difference is the predicted class angle minus your test image angle. You ran 360 tests, and say for this example, the first one wasn't rotated at all, okay? And so it came out, your model predicted that it was 0, okay? And over here, your image, your test image, wasn't rotated at all. It started out just randomly. It was at 40 degrees. Now, I mean, let's say you come in and we rotated 10 degrees, and the concept here is the model should predict, like, oh well, this is actually, the result is 10 degrees. So our difference is going to be 40 degrees. So in a perfect world, all 360 results would come out to, a difference of 40 degrees. And that's not going to happen. So what we want to do is for each 360 of those tests, we want to get the angle difference with the highest result, and say that comes out, to a 38, a 39 degree difference, and that is what our output is for the model. So at this point, you might start doing the math in your head and start thinking, well, you got 20 seed models, you got 300 coins to group, we're doing all these tests, and like, whoa, all of a sudden, we're up to over 2 million images we have to inference. Luckily, these are tiny. 28 by 28 images. You can get them moving through a GPU really quickly, 40,000 a second or something like that. So this is a really quick process. A few things before we wrap up this video I wanted to talk about a little bit. I see this being used in all sorts of machine vision and robotic vision applications where the parts are very similar. One of the reasons I'm out there publishing this stuff is I don't see machine vision being talked about very much when it comes to deep learning. My experience has been that deep learning is very easy for machine vision to the point where you could do these things unsupervised, or you do it with a very small number of labeled examples, and that's really useful. Where the engineer doesn't have to spend time writing software, and you don't have to label. It's very important, big time saver in that area. Okay, so a more generic term for this would be graph-based correlation. This is one of your tools that you can use in the unsupervised world. Graphing is a computer vision term talking about points. I haven't done it, but I've done it a little bit. This would include positional correlation, which I think is even more powerful. Where you window over and you do the same sort of thing in X and Y. And also using this technique, you can get things like heat maps. That's where you get into anomaly detection. So graphing is a mathematical term, and one other thing I wanted to point out is positional correlation. I'm talking about a subpixel localization of areas. For example, a specific feature on a coin, whatever, a date, a building, or whatever. It'd be really nice, to get in there and to get down to point, a 0.2 pixel or 0.1 pixel of where that is, and to be able to match that up with other coins. One thing that's done a lot is object detection and localization. Talked about a lot in deep learning, but that is not of the precise locating that I'm talking about here, that I'd like to do. One last note: I have been using the whole image. I think it'd be better to, I got to test this out, to try to take patches in a circle and to correlate those crops as well. Say, for example, we took, let me see here, number of items, 36, angle of fill, 360. Okay, so say we took a patch every, so often, and we trained on that. I think there's more data here since it's zoomed, that this may actually be a better approach. But as with, inventing things, one approach works. You move on. it doesn't necessarily have to be faster at this point, but I think this might work better. So that's all. If you got any questions or comments, please put them in the comment section of the video, or you can contact me directly, or you can place issues in the GitHub repos. Whatever, just get a hold of me. I mean, I love to get feedback on this. You know, I mean, I love to see what other people are doing. I get a lot of neat emails and calls. Makes for some interesting conversations. So check out the rest of my videos while you're at it. I mean, there's a lot of neat stuff in there. So y'all have a good day.